Hello, my name is Mason Sharp, and my project is about Newton's method. We're going to be able to see how it works through some examples, and we're going to be able to simulate it through code coming up. So, let's begin. The first, what exactly is Newton's method? Newton's method is a fast and simple way to get the approximation for where f of x is equal to 0, aka the root of the function. This means it will find the point where the graph touches the x-axis. Here's the x-axis, and this is the point where it touches it. It does this by taking multiple tangent lines at different points that slowly take you closer to the root that you're looking for. As you can see here, first it's the blue, and the second's the green, and it gets closer to the root. So before we get to the proof of Newton's method, which I'll get to, first let's go over how you use it. First step, pick a number for x. This can be any number. Preferably, it should be an educated guess. That's as close as you can to the result. Plug that number in for x into the equation. X minus f of x divided by f prime of x, or the derivative of f function of x. As you can see here in this right equation, the answer to step 2 is your new x. So then you just plug it back into the same equation, but with the new x from what you got from this equation. And you just keep repeating the process, and it should, if everything goes correctly, take you closer and closer to your root. One flaw with this strategy is that sometimes it can take a lot of iterations to get to the root that you're looking for. It can be really annoying, but with the power of code, it can be a lot easier. Remember in class how we talked about that this could be done automatically by computers? Well, I decided to go along and try and take that challenge for myself. And this is the result that I accomplished. So here's the interactive simulation. It may look a little confusing at first, but don't worry, it's not as complicated as it looks. In the top left, we have our equation. Right now it's x squared or x cubed plus x squared plus x plus 1. But here we can change our equation, so we can get rid of the cube term. We can make it like 4x squared, and we can change it from plus to minus, and so on. See, we got that. Then on the right here, we can find the different iterations automatically. So if we have just like something simple, like 1x minus 3, start at like 4, something like that. So here we have our first point. Let's find the next x. Goes down to 3.18, and so on. I just keep clicking this button, and as you can see, it's getting smaller and smaller until the difference is barely even noticeable. And you can see it's right about this 1.73, and this is going to be where our root is. One other thing I've went along and done is made it so that it graphs itself. So if I press space, it should come along here. Yep. Here's the graph of the function played out in real time. You can see this is an x squared function, so we got a parabola, and it goes through that exact point right where the x-axis is. Pretty neat. Now let's look at a real-world example, finding mass amounts of roots all at once. Imagine working for some math-related company. You need to find the roots of a function given a large array of constants. So, for example, say you were given a task to find the roots of x squared minus c, with c being all whole numbers from 1 to 5, so no decimal numbers. With this program, it becomes a lot easier. Before, you'd have to calculate them all individually. It'd be a bit of a pain, but not here. So let's see what that looks like here. We already kind of have it set up. Let's start at x squared minus 1, and then let's choose 2 as our first number. Let me get rid of that. It's 2. I just keep pressing the button. You can see that it kind of flip-flops between a little over 1 and a little under 1. It's a little interesting. Let's, for an experiment, let's try and set the first x to 1 and then do it again. And look at that. Every single iteration is 1. So that would be, and if we do the graph, As you can see, it's going to go right through 1. Yep. But let's speed this up a little bit. Let's go x minus 2 now, then 2, go through them. Looks like we've got 1.41 minus 3, put it again, 1.73, bam, next one. Look at that, we got 2 now. Bam, -5, or not 45. One last time. And this time it's going up a little bit to 2.23. So that's all nice, but what exactly was I doing in terms of quote-unquote Newton's method? Well, so first we chose 2 as our guess, and we had 1 as our constant. So if you plug the numbers into the function, or 2 into the function, 2 squared would be 4, and then minus the 1 would be 3. Then we figure out the derivative of the function, and since it's just x squared, that would just be turned into 2x, and then the constant goes away. So it would just be 2x, which would be 4. Then if we put all those two things in for the Newton's method equation, which we saw earlier, then it would be x minus the function divided by the derivative of the function, which would be 2 minus 3/4, which would be 5/4. And then we have then we just repeat it. And that's exactly what we got with our graph from earlier. There's a bit more to explain with Newton's method, though. Let's try and figure out the proof for why this works. So, how it works is first we have to find the tangent line of a random given point on the equation. This is our guess from earlier, like what we put in for our first x. Then the y of that point would be the function value of it. So the first point is x1, comma fx of 1. The tangent line is represented as the derivative of the function. Since we have a point and a slope, which we just got, we can turn this into a point-slope form. So take this, and then as you simplify it down, it becomes y equals f prime of x times x minus x1 plus f of x. Then, for our next step, we need to find where the tangent line crosses the x-axis, aka where y equals 0. And this will be our next x that we test. So we plug in 0 for this equation here. So 0 equals all of this. Write that. And then we pretty much just solve for this x that we're looking for, right? This x that doesn't have a number next to it, not the x1 that we guessed earlier, but this new x. This is going to be, again, what we're trying to solve for. So first, we subtract the f of x on both sides to get rid of this. Then we divide both sides by the derivative of f of x, which you can see here, we're getting rid of this part. And then finally, we add x1 to both sides, so this cancels out. And this gets x on its own. In the end, we get x equals x minus 1 minus f of x divided by the derivative of f of x, which is Newton's method. We call this new x x2, and then we continue with this x2 being the new x. Before I end off, here's some quick final things about the simulation that might be nice to know. There's a settings page in which you can manipulate lots of the different parts of the yellow line part of the graph equation, like how fast it goes, the minimum and maximum that it'll allow, that'll print onto the screen, and the scale of the squares. You can see here that each square represents 1 unit of space, pretty much, but we can change that to any number we want. We can also hide UI and stuff. We can see if I redo this, you can see it's a lot thinner and it goes a lot faster. Very neat. But that is all I have to show you today. And here's the bibliography. I used the Desmos graphing calculator for some help. The Unity game engine is where I made the simulation in. And the calculus book for providing some additional help and informing us about Newton's method. Thank you so much for listening. I hope you learned something new.